Hello, 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 good afternoon. Good afternoon. Thank you, Vanita. All right, good afternoon, Vanita. Hello, good afternoon. Oh, here we go. All right, here we go. Hold on. So, yes, good after. Oh, a lot here. Okay, good afternoon, Genesis. Good afternoon, Chastity. Good afternoon, Gabriella, with an exclamation point. Awesome. Good afternoon, Ariana. Good afternoon, Direct Chat. Good afternoon, Brian. Hello, Carlos. Good afternoon, Kaya. All right, now we're going. Isn't this the class? I thought this was like the total video class. Maybe not. All right, it could be it. Good afternoon. Okay, so oh, and we're okay. It is cold. Okay, so let's get going. As So, of course, you can ask questions at any time. I mean, if there's any questions from hello, sorry, good afternoon, Brian. If I didn't say hello, Carlos. If I didn't say good afternoon, Kaya. Um, if there's any questions at all from last time or from the class in general, for the class in general, please feel free to ask. This is a good time to ask. Okay, if there are not, oh, people are still coming in. If there are not any questions yet, I mean, certainly ask them at any time. Um, but what we're going to do now is we're going to continue going over homework one. There it is. We're going to continue going over homework 1A. We're going to start going a little faster now. That is, again, the whole emphasis of the last class was to use question one to very methodically walk through the 5-step problem solving method to show that it is that important to me. It is that important to the class to do things with the 5-step method. Um, but now that I think it's established, or and you have that you have an example for it, I want to move more and more into the physics. So I won't always do all of the steps when I'm trying to teach you something. Um, but that doesn't mean that you don't. Um, so today I'm going to try to get through more of the answers and the physics concepts of homework 1A. Couple things about that though. First of all, we're still not going to finish it today. We are not going to finish. We're not going to get to question 9 today. We never do on the second or third class. So just please understand that going in, like again, that homework 1B, homework 1A is meant to introduce a lot of the concepts, big concepts that we need for the rest of the course. And it's meant as an opportunity to review and refresh and unpack some of them. So it always takes us a while to go through to go through homework 1A. So just know that. Therefore, you, over this weekend, you still have plenty of time to incorporate anything that I do in today's class that helps you at all to improve or revise your work on homework 1A. By all means, spend your time this weekend or whatever revising or uploading and improving and re-uploading any draft of homework 1B, whether or not you've gotten feedback so far, homework 1A, I mean, whether or not you've gotten feedback, feel free to do that. In the meantime, we still go on to homework 1B, but please note this, the homework 1B, which is due next class, I believe, homework 1B does not in any way rely on a completion of homework 1A. Like that's on purpose. I just want you to know that homework 1B is due next Monday. Where you are with homework 1A, homework 1B ought not be stressful or mathematically involved. In fact, I should say explicitly, homework 1B is the one exception to all the expectations and rules regarding the 5-step problem solving method. Like you don't have to do the 5 steps for homework 1B. You most certainly do for homework number 2, but you do not for homework 1B. It's like a thought experiment. It's meant to be a little bit relaxing. It's kind of like, for those of you who took Physics 203 with me, I mean, it's a little bit like train of thought in that it's, it's to get us, our thought processes going in a certain direction. So it's meant to be enjoyable, not meant. Okay, so do homework 1B for Monday. Don't worry, and keep revising and uploading homework 1A, but don't worry if you're still struggling with like question 9 of homework 1A, because homework 1B does not rely on that. Okay, I hope that's sort of clear. Oh, good afternoon. Okay, so is there any other logistical thing I needed to say? Remind me if there's anything logistical I'm forgetting, but if that's the case, I'm now going to go back to homework 1A. Yes. So I believe, oh yeah, with this class, yeah, we had walked through question 1. Then I think we had time in this class where I sort of just gave you answers and then like a hint for question 2, 3, and 4. Stop me if I'm wrong about that. But yeah. So anyway, here on the board right now is the answer to question 1, which we already got. Okay. Then the answer to question 2. Notice I'm not showing you all the work. I think it's sort of straightforward for question 2. You still have to for me, but I'm not for you. So question 2, the answer is acceleration is negative 100 meters per second squared. I do believe that you would get a negative sign there, assuming that you, like me, and I should have put this actually in the diagram. Excuse me. I'm assuming that to the right is positive and to the left is negative, or I'm making that choice. You could make a different choice as long as you're consistent with that choice. But frankly, I'm also making that choice because the problem says that the initial position of the mass is 0.15 meters, right? It doesn't say negative 0.15 meters. It says point. So I'm calling the right side, positive. Therefore, if we do that, then the acceleration is definitively negative because the mass is accelerating toward the equilibrium position. At the risk of doing a spoiler alert, I should make clear also that that negative sign does not mean that the mass is slowing down, right? Like this is like a physics 203 concept. It's negative acceleration because it is accelerating in the negative direction. It is right. I'll just leave it at that for the moment. Yeah, I mean, it is getting faster and oh, there she is. Okay, awesome. It is getting faster and faster in the negative direction, is what that negative sign means. Right, so I'll leave it at that for the moment, but I hope that's clear. But the negative is part of the answer. All right, so that was question 2. Then question 3. Again, I'm not showing all the work. I'm not doing the steps. You need to do the steps. If for no other reason to show that you actually understand it and you're not just copying from me, okay, blah, 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 blah. But what answer do I get uh, for at the position x equals 0, the instantaneous acceleration is 0 meters per second squared. Now, I think that's just a plug and chug as far as the math is concerned. Again, please stop me if you have an issue with it. But yeah, I mean, I think it's basically, I plugged in 0 for x, so I got f equals negative k times 0. So I get f equals 0. So then I get do F net equals MA. So I get A equals 0. Fine. But 2 quick observations about that answer. 2 quick observations. One, just notice that question 2 and question 3. Okay, first of all, question 2 and question 3, hopefully, and question 1, hopefully they weren't super stressful. Hopefully. But what sometimes happens to physics students is if a question at the beginning of a problem, at the beginning of a sheet, like seems somewhat straightforward, sometimes people are so used to physics being hard that then they think it must be a trick question or they overthink it or something like that. Like, please let me remind you that especially if a problem is a multi-step problem, frequently in physics, the early steps, the early parts of that multi-part question The early parts are often comparatively straightforward. They're not tricks, and they're also not meant to waste your time. Don't overthink them. Frequently, the reason for early questions is that we're trying to break down the whole thing into a number of steps. And so we're at the beginning asking for information. We're not asking because we think that the information's that hard to get, but we, in fact, think that the information's somewhat accessible and will be very useful for the big punchline that we're going for at the end of the problem, right? So where am I going? So hopefully you got the answers, negative 30 newtons, negative 100 meters per second squared, 0 meters per second squared. But now, like, why did we just bother with this? Because one thing to note is question 2 and question 3, we just asked the same question. What is the acceleration? But we asked it about 2 different spots, 2 different positions, and we got 2 different answers. So right off the bat, let's notice the acceleration in this situation is changing continuously from place to place. Why? Because the force is changing continuously from place to place. We don't have constant acceleration in this situation. That's partly what question 2 and question 3 are trying to signal us. This is a non-constant acceleration scenario, okay? Specifically, so the acceleration is changing. It's not a constant. Hence, a lot of relationships or pieces of knowledge that we might have acquired in physics 203 that assume constant acceleration, like, are now not going to be as helpful anymore. That's part of what's going on here. Let me also note, however, before I go on, that it's not just that the acceleration is changing, or it's not just that force is changing. I mean, we're used to changes in physics, but notice that the acceleration and force are changing, like, as a function of position. Like, what's driving this problem sheet, this homework sheet, this whole scenario is the equation F equals negative kx. I just want to note that that's a very simple looking equation. It is. It's nice and simple. It's, as we pointed out yesterday in last class, it's a linear equation. It's not F equals negative kx squared or something like that. I mean, it's a direct proportionality. It's nice and tidy, but make no mistake, it's F equals negative kx. It's not F equals negative kt, for example. Like, what's happening here, just before I go any further, is why this is our first homework in this class and why it's a big homework is we're starting the semester by making a subtle shift to where space, position, is now kind of acting as our independent variable rather than our dependent variable. That's not what we're used to from physics 203. We're used to things depending on time, things such as position. Now, things are depending on position. That is a shift in perspective, or in emphasis. That's just worth noting. Okay. Okay. Now, second thing to note about question 3, about the answer to question 3, is that we get A equals 0 at x equals 0 at the equilibrium position. I want to point out to you, that is, in fact, not just an observation. That's not just a coincidence of this problem. That is actually what it means to be an equilibrium position. By definition, equilibrium in physics in general, but I would say probably even in science in general, a position of equilibrium balance means that all the forces acting at that position are in balance, are equal to each other. So by definition of equilibrium, F net equals 0, thus A equals 0. Why am I making a big point of this? Because to my mind, well, first of all, it's correct. I mean, it's correct. It's what equilibrium means. It means A equals 0. But it's also, when you really think it through, it's a little bit of a wake up, because if I didn't realize that explicitly, I would have always thought, I did always think half consciously, that equilibrium meant a place of no motion. It's very easy, unconsciously or half consciously, to think of equilibrium places as static places, as stable places, as places where things don't move. I don't want to overdwell on this, but I want to say, that's not right. That's what people tend to intuitively think. But an equilibrium position is not necessarily a place where something can't move. In fact, we're about to get to question 4, of course. Question 4, the whole premise of question 4, I mean, is that this mass, once you let it go from out here at 15 centimeters from the equilibrium, you let it go and it starts moving and moving and moving toward the equilibrium. It's moving toward the equilibrium. When it gets to the equilibrium, it doesn't stop. The whole premise of question 4 is that it has a bunch of speed when it gets to the equilibrium. And we solve for that speed in question 4, and we don't get 0. We get a number, we're going to get a number that indicates this thing keeps on going. It may be moving toward the equilibrium, but when it gets there, it passes through the equilibrium and keeps going, just like pendulums do, right? Or just like the situations in the lab do. Equilibrium does not mean no motion. Equilibrium means no acceleration, which means, and then I'll be done with this, which means, sure, since an equilibrium spot is a place of no acceleration, you not only can you have motion at an equilibrium spot, but we tend to have maximum motion at the equilibrium spot. We're going to find, if you didn't already realize it in this homework, like whatever number we get for speed for question 4, whatever number we get for the speed at equilibrium there, that's like the highest number we're ever going to get for speed throughout the whole problem. So equilibrium can mean, usually does mean, maximum speed. The thing about equilibrium is, since it's a place of 0 acceleration, that means if you put a mass at equilibrium, equilibrium is the one and only place that if you put something there with no motion, if you place an object at equilibrium and give it an initial speed of 0, well, then because its acceleration is 0, then its speed will stay 0 forever. So equilibrium is the one place that if you do put something there, it will stay there, unlike any other place, such as x naught. And that's why people think what they do about equilibrium. But okay, bottom line, from here on in, don't think of equilibrium positions as places of no motion. Think of them as places of no acceleration and quite possibly maximum motion. Okay, so that was question 3. Is there any question? Okay. So now, excuse me, now we get to question 4. So now I think question 4 is a little trickier. So I am going to expand. I'm going to like revert to the 5-step method here. And again, that's what I do, right? I practice the 5-step method as much as I can in places where I think I know what's going on. And then when I'm not totally sure I know what's going on, oh boy, do I rely on the 5-step method. And I mean that seriously. So question 4. Okay, so for the diagram, okay, we have it already. I do step 1 diagram fact pattern for diagram C above. Okay, so that's my diagram, right? Okay. Then step 2, what is the question? Well, the question for question 4 is at x equals 0, i.e. at equilibrium position, what is the instantaneous speed? Okay, that's what I've been right? That's the question. Now, first of all, again, I think there's a strong suggestion or implication here that the answer is not going to be 0. I mean, look, the answer was 0. The speed was 0 at x naught. And at x naught, the thing had a major acceleration. So you think it's pretty unlikely that it's going to have v equals 0 again here. So we need to solve. So we're going to solve for speed, right? For instantaneous speed, for v. Well, the first thing, so I go to step 3. Now, maybe I don't know what to do just yet. Excuse me. Sorry. TB or not TB? That is the congestion. Okay. Consumption be done about it? Of course not. Okay. So we might think, oh, so my step 3 GDP, again, when I don't know what to do, really it's steps 1, 2, and 3 that really get me launched. So step 3, what is my GDP? what's my general definition or principle that I can use to solve this problem? Well, I might be thinking things like F net equals MA, which I used for questions 1, 2, and 3, or I might be thinking things like F equals negative KX, or maybe even more sophisticated, I might be thinking, well, I've just done all this work with accelerations in the last 2 questions, and I'm looking for a velocity. So can't I use one of my like acceleration velocity relations from physics 203 from physics 1? But the answer is no. I can't, because I just made the opposite. The whole purpose of question 2 and 3 really was to show me that acceleration is changing as a function of position. So my constant acceleration equations. Oh, yeah. Hold on 1 second. 1 second. I'm sorry. Something just came in that might mean. Oh, okay. Oh my God. Okay. Sorry. Stay from my kid's school. Um, sorry. So you can't use constant acceleration equations, um, because there isn't constant acceleration. So what we need is something that does work when acceleration changes, specifically when force changes, specifically when force varies as a function of position, right? That's what we have here. Force is changing as a function of position. So what I want to tell you is that right there signals to me that the concept of work and energy is what I now need to deploy. Oh, okay, like we're about to like start dealing with work and energy. What I and I feel like, and I've done some of that with some of you. If you had me, last semester, or if you had somebody else, I think many of you have seen some concepts and equations about work and energy and stuff, and maybe in high school. Let me take a moment to say, if my experience was, I mean, this is like a classic physics thing. My experience was when people showed me things about work and energy or said, here's a work energy problem, like solve it, I could do it. I mean, to an extent, I could do what they were saying, asking me to do. But when I got to certain points in college or graduate school where I was just given problems and then no one told me like what methods to use to solve them, but just like, here's a problem. What I never knew, when am I supposed to use work and energy? Like why, or as opposed to forces and acceleration, or as opposed to like momentum or something like that, like other conservation principles that do arise in physics. My whole thing was like, I don't know when to use what. Like, how do you, once you show me I'm going to use work and energy, I follow, but how did you know? Here's how. I want to emphasize, and we're going to do this in detail later, but hopefully you remember vaguely that work is force times displacement. I mean, really, work is the integral of force with respect to displacement. We'll do that. We'll review that again in detail shortly. But the fundamental point is that what work is force acting through space. The whole reason we ever care about work, well, and what does work do? It transfers energy. If I push you through space, then I add kinetic energy to you, right? Like that's like the point. Why do we ever care? When do we know to use that concept? Precisely when we have situations for which the force is varying as it acts through space. That's the whole point of work and energy. So um is that a oh,
I need to go too.
okay, sorry, hold on. I think that's a mistake. I think I'm gonna mute this.
Slap him.
Okay. So I'm gonna cut to the chase. Like, but yeah, so whenever you have a force, whenever you don't have constant acceleration or constant force, and specifically when you know that force is varying as a continuous function of space, of position, that is a signal right there to use the concepts of work and energy. That's how I know I'm going to use them right here. Okay. So my GDP, I'm going to write it first as English, and then I'm going to write it mathematically. The GDP is when force varies as a function of position, like, okay, dot, 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 or perhaps in more elaborate terms, when all the forces doing work on a system are conservative, we say the system conserves total mechanical energy from place to place. Now, let me say a little bit about, first of all, so this is my GDP in English. My general principle here is that is as long as as long as forces are doing conservative work on a system, then the system will conserve energy. You don't have to write it exactly the way I did. Those are my words. You can, that's my English. You can use different English, but that's the idea. Second of all, some of those words are very specific and technical. Like I'm going to, I'm assuming right now that you have notes about what work means and stuff like that, or that you can refer to, or that you have a concept in your mind. So I'm just going to like finish the problem and get answers so we can all be happy. But then I'm going to backtrack. Like next class, I'm going to backtrack and remind us specifically of how to think of work in a very calculus kind of way. I will review and unpack the concept of work after we get some answers. Second of all, I want to say very specifically from a calculus perspective what I mean by a conservative force. I mean, the quick thumbnail sketch is that like this spring force is a conservative force. Gravitation is a conservative force. In very rough terms, forces that depend on position, forces that vary as a continuous function of position, are known as conservative forces, and they're conservative in the sense that they tend to that they do a total amount of zero work for any round trip. I mean, again, I'll do this in more detail on Monday, but a conservative force is a force that does positive work in one direction and then negative work in the other direction. So it always ends up giving you back anything that it took from you over a round trip. That's what a conservative force is. Such forces, when they do work, well, they accomplish what I just said. They maintain a constant amount of energy for the system that they're working on. Okay, again, that's the principle. That's the thumbnail sketch. We'll unpack it in more mathematical detail next week, but that is the principle for step 3. And I'm going to write it mathematically now on the next page. But one last English thing to say about it. When we say that energy is conserved, that conserved means maintains the same amount, maintains a constant amount, right? Something that I didn't get forever until I did is systems that conserve energy, and this is one of them. I mean, the mass on the spring system is a system that conserves energy. What does it mean to conserve energy? It means to maintain the same amount of energy from any one place to any other place. Very specifically, well, here we go. Mathematically, when we say the total amount of energy is the same, we mean from here to there. That's what we mean with that. And it's not a coincidence that we mean that, because the whole idea of energy and work is that it's a concept that we apply when forces are varying as a function of space. So one way, well, okay, so mathematically, what I'm saying here for our step 3 GDP is the total amount of mechanical energy at any one X value must be the same as the total mechanical energy at any other X value. Specifically, total mechanical energy, like capital E, total mechanical energy is defined to be all of the kinetic energy plus all of the potential energy of a system. That's the definition of total mechanical energy, is all kinetic plus all potential. Now, in this case, I mean, just to cut to the math again, kinetic energy in classical physics is always 1/2 mv squared, always. If you ever wanted a memorizer, that's a memorizer. in classical physics, that kinetic energy is always 1/2 mv squared. Potential energy is a more subtle concept. Potential energy, and frankly, I'm not even sure that everybody in the room has seen potential energy in college yet. Again, I'm going to go back and expand in sort of more detail mathematically and calculus wise what I mean by potential energy. Potential energy is it means stored energy, and it's a concept that only applies to conservative forces. Conservative forces do the same amount of negative work in one direction as they do positive work in the other direction. So, by definition, so conservative forces, any amount of work that they're doing on you, any amount of kinetic energy that you're ever losing under the activity of a conservative force, we can always say, wait, you're going to get that back on the way back. Like I'm going to say this again, even though I will say this next week. A conservative force, by definition, is a force that does zero work, zero net work around any closed path, any round trip. That's what a conservative force is some forces do that and some don't. But a conservative force is one that for any round trip will do a total amount of zero work, i.e., it does positive work when you go in one direction and it does negative work in the other. Okay, quick sidebar. You might think that that's always true of all forces, but it's not. If you think of like friction, no matter what you're doing, friction's always doing negative work, right? Because no matter what, okay, I don't want to get like rabbit holes, but I mean, if work is force times displacement, and if positive and negative signs matter, then when you're acting under friction, whatever, if you're going north, friction's pulling south. But if you're going south, friction's pushing north, right? So friction's always acting against displacement. So the total work that friction's doing is always negative. So friction is not a conservative force. It doesn't give you back what it takes away. However, gravity and spring forces are conservative forces. Whenever a force, so with conservative forces, whenever you seem to be losing kinetic energy because you're traveling in a certain direction, we can always say that that energy is being stored up for later. What later? Later when you go back in the other direction and complete your round trip, right? We can always say that energy that you seem to be losing in the form of kinetic to a conservative force is actually being stored for later in the form of potential. Now, and again, I'm going to discuss this all again next week, but like, I don't know if that's really happening in nature. I mean, where's the energy being stored? I would say it's being stored in our mind. Right? Arguably, potential energy is like a bookkeeping trick that we're doing in our brain just because we're so confident that everything's going to work out at the end of a round trip under a conservative force. So anyway, potential energy function. So the potential energy that is stored while a conservative force is doing work, what potential energy really is, mathematically, is a prediction of how much work the conservative force will do to bring you back, to bring the system back to equilibrium. So it varies, the potential energy function varies from one force to the next. In the case of a spring, the potential energy function is 1/2 kx squared. That's why I have written what I have written down here at the bottom of the page. Okay, what I'm saying to bring this back to reality, I'm saying the GDP, the step 3, is in general, if all the forces doing work on a system are conservative, then then any amount of kinetic energy that ever seems to be lost at any given moment is being gained in the form of potential energy. It's just being stored for later if it's a conservative force. So we can say that the total amount of kinetic plus potential that you have at any one given spot is the same as the total amount of kinetic plus potential that you have at any other given spot. So in the case of a mass on a spring, what that means mathematically is 1/2 mv squared plus 1/2 kx squared over here must equal 1/2 mv squared plus 1/2 kx squared over there. Now, in principle, I just explained the whole thing in principle. but that may have gone way too fast for some of you, understandably. And I still didn't, and I'm just saying for the moment, 1f kx squared is what we get if we try to solve for the work that a spring does. The work that a spring does to restore a mass to equilibrium. I'm asserting for the moment it's 1f kx squared. I will totally explain that using integrals next week. But so fear not. But just so we can make some tracks in the meantime, my GDP then for this statement, for the motion of any mass on any spring, is just this right here at the bottom of the page. 1f mv squared plus 1f kx squared over here must equal 1f mv squared plus 1f kx squared over there. So like x1 and x2, it's true for any x's that I pick. Oh, okay. And I will turn the page. But so notice, this is like a speed to spot correspondence. Like the bottom line is that the question was saying, what is the speed at a certain spot in this situation? By spot, I mean position, point in space, right? It's asking, what is the speed at a certain spot? And it's assuming that you know the speed at some other spot, which you do. Like you know how fast it's going at x naught equals 0.15 meters. It's going 0, right? So it's not asking you to relate speeds to times. It's not asking you to relate accelerations to times. It's asking you to relate speeds to spots. First of all, that did not tend to happen in Physics 203. I'm just saying. Second of all, I am now the summary of everything I just yammered for 10 minutes. The summary is if ever you get a question in physics where that's involving a speed to spot correspondence like this, you know the speed at one spot, you need to know the speed at another spot, or you know the spot for one speed, you need to know the spot for the other speed, then that definitely is a signal to you that you need to be doing work and energy analysis. That's what we're doing here, okay? So all of that was my explanation of GDP step 3. Would you provide that much explanation in your homework? No, you don't have to provide that much explanation, but I do want to say, follow my model that the first time you ever introduce an equation in a document, this is for homework, for exams, for research papers, for journal articles, like the habits I'm trying to get us all into, especially now that we're in Physics 204. The idea is in a document, in a self-sufficient physics document, the first time you introduce an equation, even if you think it's totally obvious, or you think other people should think it's obvious, or whatever, if it's the first time you're introducing an equation, it's good to over-explain it with context and English and background. Like you always want to show why the first appearance of an equation actually makes sense and comes from somewhere. It's not just out of a hat, right? Then once you've explained it once, then you could just like keep using it. So you don't have to do everything I'm just doing here, but do some version of overkill. For the first time, we're establishing this. Now we've established it. So this that we've established is 1f mv squared plus 1f kx squared over here equals 1f mv squared plus 1f kx squared over there. It's true for any two given spots. What two spots should I pick? I should pick a spot where I know the speed and compare it to a spot where I'm solving for the speed, right? One is the known and the other is the unknown. So here we go. So now I'm in step 4, right? Now I'm starting to apply this principle to the actual problem. So I've picked my two spots. My spots are the equilibrium position where I'm solving and the initial position where I know everything, right? So what do I first do? First, I look at it and I'm trying to postpone numerical calculations for as long as possible, right? That's a strategy, especially for Physics 204. It is a strategy. I mean, it's a strong suggestion from me, but I know a lot of us like to just put in numbers immediately as fast as we can because for a lot of us, it's more concrete to picture numbers. I respect that. Like I certainly sympathize with that, but it's actually a habit that we want to grow out of. We want to start thinking of this as not about numbers, but about letters. More and more, the numbers are just going to drop out. We're just looking at abstract physics relations. So we really want to get in that habit of doing any algebra or trigonometry or calculus like that we can before we plug in numbers, also the other advantage, so that we're doing physics. not just math. And the other advantage is, in case quark forbid, you should maybe make a computation error on your, or you do something wrong on the calculator or like orders of operations or something. If you postpone the numbers as long as possible, then the error won't bleed through all your work. You know what I'm saying? So it's a good habit. So that's what I'm doing here. So, okay, so I just start analyzing. I ask myself, I look at the left side. The thing in yellow, I'm just reminding you, like V, where I circled the V in yellow and like pointed to the X equals 0. That's just a reminder, like that's what I'm solving for, right? I'm solving for V at position X equals 0. So I ask myself, well, so I don't know what that V is, but the X, I mean, but if X is 0, then that entire term, 1 FKX squared, equals 0, right? In other words, at the equilibrium position, there's no potential energy. At the equilibrium position, all of the energy is kinetic. When the thing starts off at X naught, that's when all the energy is potential and there's no kinetic, right? So I can cross off that term on the left-hand side, make it 0. And similarly on the right-hand side, when X equals X naught, when it equals 0.15 meters, the V is 0. So I can, there's no kinetic energy. So I can cross that off. So notice that I get 1 F mv squared equals 1 F kx squared. Let's pause here for a second. This, notice, that looks very familiar to a lot of people. Like, that is not a step 3 GDP. That is a result of step 4. This is like the difference. This is one of the reasons I care about the steps. This is one of the like a difference between triple equal sign and double equal sign. Like it says 1 F mv squared equals 1 F kx squared. Be very careful about that. I mean, we'll see, particularly in the next question, how important it is to be careful about that. But what I'm trying to say is, it looks like that's saying, oh, kinetic energy equals potential energy. That is not what we're saying. All the kinetic energy over here at equilibrium equals all of the potential energy over there at the initial position, right? We're not saying, that is not saying that we're looking at a spot where the kinetic and the potential are balanced. That would be a very specific spot that like nobody's asking about here. We're saying, so our principle here is the total amount of energy over here must equal total amount of energy over there. If you happen to look at two extreme points, which we happen to be looking at right now, we're looking at two extreme points where in one case, all of that energy is in the form of kinetic, and in the other place, all of the energy is in the form of potential. So those two lumps are equal to each other. I'll just move on. But what I'm really trying to say is that step in the middle of the page is a step. It is not to be memorized or considered a law or something like that. Okay. So, okay. So there we got to it. It's a step. So then I multiply both sides by 2, cross that. I'm solving for V. So I'm not putting in the numbers yet. I'm just like rearranging everything and solving for V. So I get V equals square root of KX squared over M, right? Right. Stop me if you want me to. Wait, I'm looking at the chat. Okay. There's nothing in the chat. So I turn the page. So V equals square root of that. Then now I'm going to start plugging in numbers. And by the time I'm plugging in numbers now, I'm like, look, when possible, I look at my units. Well, certainly I'll look at scientific notation if there's any scientific notation to look at, but I really do try to track the units. I mean, sometimes it's just way too cumbersome to do, but if it's at all reasonable, I track my units because it's like a check. It's really a good check on whether my work is making sense or not. Like, and it keeps it from just being raw, abstracted math. It keeps it a science, right? So I put the units in and I say, the stiffness of the spring is 200 newtons per meter. The mass, excuse me, the initial displacement of the mass is 0.15 meters, and that gets squared. The mass is 0.3 kilograms. Okay, and then I like a little check to myself that like on the top of that whole square of that whole fraction, I've got newtons times meters, right? I mean, I have newtons per meter times meters squared. So I have newton, so one of the meters cancels. So I have newtons times meters over kilograms, right? And what is a newton? A newton is a unit of force. F net equals ma. So a unit of force is a mass times an acceleration. So just checking the units here as a kind of a sidebar or as a check or triangulation, like what I have in the numerator is kilograms times meter per second squared times meters, right? Right. So I have kilograms times meters squared divided by seconds squared all over kilograms. So the kilograms cancel and I have meters squared divided by seconds squared. Well, that's very nice because it's all under a square root sign. So it's all going to get square rooted and make meters per. Sorry, I didn't realize I had that in my ear. I promise I wasn't listening to anything. It's just really weird. So I get meters per second. Can you imagine if I was while I was doing this? That'd be crazy. Okay, sorry. So I had the square root, but it kind of is like that, isn't it? The fact that I'm having, no, I'm just kidding. Okay, so I have square root of meters squared per second squared. That makes meters per second. Does that prove that I'm correct? No, it doesn't prove that I'm correct. I could be off by a constant length, but it certainly strongly suggests that I'm on a good track. And conversely, if the units didn't work, I would know something was wrong, right? So it's just like positive affirmation or like checkpoint that I'm doing okay. Okay, so anyway, so I get all that. So now I plug in the numbers, and one last thing. Well, yeah, I plug in the numbers, and one thing to be careful about is I look at the wording. Whenever I have a square root, and this is going to happen twice, right? I mean, it's going to happen again in the next problem. Whenever there's a square root, as a physicist, I should pause and ask myself, what square root? Like sometimes there really are two roots, like a positive and a negative. Technically, I'm solving a quadratic here, right? And quadratic mathematically always has two roots, and they always mean something. The math means something in the physics, but whether I care about both the roots or not depends on the phrasing or the context of the physics question. So in other words, I got to ask myself, do I care about both the roots here or not? And I look at the question, and the question says, the question actually says, hello. Oh my God. The question says, and meters per second, at what instantaneous speed does the mass travel through the equilibrium position? So it's asking about what's the speed. Therefore, I only care about the positive value of any answer I get from this square root, right? Like, it, okay, I don't want to rabbit hole this, but well, okay. So, when I do out the numbers, I get approximately 3.87 meters per second. What I'm trying to say is that if I were literally solving for velocity, right, I would actually get a negative as an option. And the truth is that would be the right option to pick, right? If it literally asked what's the velocity, at least um, for this quadrant of the motion, the velocity is really negative because the thing is heading left, right? I mean, if that's what we're talking about here. So that would be the correct answer to, but it didn't ask that. It just asked speed. So I'm saying positive 3.87 is the answer. And so I circled, oh, and I forgot to write. So that's the answer. In fact, I should say, hold on one second. So that's the answer. I'm going to pause for a second. Well, first of all, look at that and see if you have any questions at all. I'm going to pause for a second also because something just keeps coming in. 1 second, sorry. Sorry. Okay, so let me just look in the chat to see if you're good with that. I'm going to go on. So you're good. Okay. So is everybody good? Okay. This means I'm going to, I forget this is that class. So I'm going too slow. We're fine. I mean, in other words, we're fine. Oh, yes. I'm looking at you one video. No, are we fine, Andy? Okay. We're fine. Okay. No, you don't have to. That's so rude of me. All right. No, but we're fine, right? We're fine. Okay. I'm moving on.
I'm good personally, but I don't know about the others.
No, that's fair. I should never make any one person speak for the others anyway. But see, that's what happens with the video. No, no. All right. All right. No, thank you. I'm just being silly. But yes, I'm going to move on to the next one. Right. Okay. I'm going to move on to the It gets so noisy in there sometimes. Sorry. The quieter I'm being, the more noisy you know it is. Okay. So I'm going to the next one. Okay. And I'm going to try to cut to the chase. Okay. Question. I mean, the diagram, same diagram. The question, did I not even write it? Oh, yeah. So question 5, see step 1, see diagram above. Step 2, the question now is assume that V equals 3 meters per second. Like, what is X now, right? Okay. So look, this is the same question as question 4. As many of you realized, of course, this is the same question, just reversing the type of information. This is once again a speed to spot correspondence, only now like we're saying the speed, we're asking the spot. So certainly now in your document and my document, it's fair. We've established the whole concept already. So, or if this were a journal article, like we've established the concept. Now we can use the concept. There's the concept. What is the concept? The concept is total mechanical energy over here equals total mechanical energy over there, whatever here and there are, right? So the concept is 1 half mv squared plus 1 half kx squared over here equals 1 half mv squared plus 1 half kx squared over there. That's the concept. If there were to be anything that you would memorize or something, it would be that. Notice, well, okay, and I'll go one step further. I'll go one step further. Always we're comparing a spot where we know the information to a spot where we're solving for the information, right? Well, we can again, as our known spot, we can again use x equals x naught, like on the right side. I have there, just like we did before, we could use x equals x naught as the known place. Or if you want, you might have done it differently. Since we just figured something out about x equals 0, we sure could now use that as our known spot. That's fine. Advantages and disadvantages, that's fine. But for the unknown, for the spot that we're solving for, right, we're now literally solving for x. Like x is not specified. Like that's what we're looking for is what is x? What is x when or where v equals 3, right? So if we're thinking about the first the first quarter cycle of this thing's motion, if we're right, like the thing started at v equals 0 over here. It started at v equals 0 at x equals 0.15 meters, and it starts coming in, moving faster and faster and faster until it gets to the equilibrium position with an instantaneous speed of 3.87, right? So the question's asking, where is it at a speed of 3? Well, presumably somewhere in between. I mean, somewhere between 0 and 3.87, 3 is going to occur, right? So I'm presuming I'm going to get some kind of answer between 0.15, between x equals 0.15 and x equals 0, right? But again, before I go any further, so I mean, so if I get an answer like x equals 0.27, that is definitely wrong, right? Because like the thing is never farther out than 0.15. So we certainly should not get an answer bigger than 0.15 or an answer that's smaller than negative 0.15, right? And while I'm on that subject, isn't this a case now where actually technically we are going to be on the lookout for more than one answer? Oh, yes, let me get your question 1 second. Let me just spit this answer out. See, now this is my revenge. This is her revenge on me for, yeah, right. Okay, hold on 1 second. Let me just say this time, since the question says where is a spot such that the instantaneous speed is 3? I mean, I believe that's what the question says. I believe there's going to be more than one spot. I believe it could happen while the thing is moving to the left or while the thing is moving to the right. And or it could happen over here on the right side of zero or on the left side of zero. So I'm going to be on the lookout for two, I believe, right? So, okay, so I'm going to be on the lookout for two answers, but pause. Sorry, word from our sponsor, Annie.
Yeah, I think you raised a good point because when I was doing my questions, like I didn't know I was getting the right answer or not, right? So now would you say that if we place the mass uh 0.15 meters away from the equilibrium point, and that point obviously is beyond equilibrium, so the spring is stretching, but it wants to contract when you release it. So if you release the mass and you just let the spring do the force, assuming that you don't apply any like horizontal force, the maximum distance the block can travel, would you say it is uh 0.15 meters towards that direction? Like it cannot possibly go long like any longer than that.
I totally agree. Okay, right. And yes, I totally agree. And partly for like because of kind of some of the things that you were saying two classes ago or last class. So yes, but also absolutely I agree with that. And this is true to everybody. Really what Andy's asking right now is question 6, I believe, of the homework. Well, I don't want to get ahead of myself, but yes, I agree that the mass could never get to a displacement greater than 0.15 ever again, because mathematically, if we believe this statement of energy conservation, if we believe the 1 half mv squared plus 1 half kx squared anywhere has to equal the same value anywhere else, well, 0.15 is the place where it has zero speed, right? Zero kinetic energy. All of its energy is potential at 0.15. So it can never have less than zero kinetic energy. So it could never be at a place of more potential energy. This is just agreeing with Annie. In other words, it's like her intuition, like just picturing this whole thing. Anybody, if you're just picturing, like, will the thing ever go past 0.15? If you're picturing, no, I don't think it will. You're picturing correctly. But now I'm here to say your picture is not just a picture. It's like literally the math is saying the most energy you could ever have is this 1 half kx square amount that it has out here at 0.15, because that's where you have zero kinetic energy, and you're never going to have less than nothing kinetic energy. So you literally never could be greater. So yes, right. Does that make okay? Okay. All right. So I'm going to start to do the math now. I think I'm going to look for two answers. So I start doing the math, and this is so. Well, yeah. So I start doing the math, and I look on the left. I'm going to do the same thing as before. Like, can I cross out any terms to make them zero? Well, I look on the left side. On the left side, the part where I'm solving for, I'm solving. So what's the v on the left side? What's the v at x? Well, the v is 3. The problem specified that at the x value that we're solving for, the condition is that the instantaneous speed is 3. So I can't cross out that v. It's 3, right, on the left side. Then what's x, where x I'm solving for? Well, it's x. I'm solving for it. I don't know what it is, but I'll tell you this. It ain't 0, because we already know at 0, at x equals 0, speed is 3.87. So I can't cross out that x. Now, on the other side, yes, I can cross out at when x equals x naught, yes, v equals 0. So I cross out that term on the right side, just like I did before. Like, yes, I cross out the 1 half mv squared term on the right side, just like I did before. But the key thing that I'm like yelling about right now, because it's kind of a big deal, is that before I crossed out the 1 half x squared term on the left side, but here I cannot cross out that term, right? So, because the spot that I'm looking for is a spot that has a mixture of potential and kinetic energy, some of each. And almost at any arbitrary spot of this entire situation. Let's go, like the whole thing starts off with a huge amount of potential energy and no kinetic energy, just like something that you hold above the ground starts off with MGH, a huge amount of potential energy and no kinetic energy. Then it starts to fall, or in this case, the mass on the spring starts to move inward toward equilibrium. So it progressively, continuously loses potential at the well, I mean, it progressively gains kinetic at the expense of, at the cost of losing a corresponding amount of potential. Why? Because in the first place, like we said 10 minutes ago, potential is just really a bookkeeping device in our mind. Potential is just a prediction of the kinetic that it would eventually get back if it went the other way. Anyway, so of course, whatever it gains in kinetic, it loses in potential. Potential was just a prediction of what was going to happen to the kinetic. So it progressively changes its mixture from fully potential to less and less potential, more and more kinetic, until it gets to the end when it's all kinetic, right? And then the reverse happens on the other side, et cetera, et cetera. So why am I saying all this? Because at the end, when what you get in the next line in step 4, you get this 1fkx squared equals 1fkx naught squared minus 1fme squared. In other words, I'm solving for x now. I take the 1fme squared and subtract it from both sides. I'm starting to do the algebra. But notice the algebra is looking a lot more complicated now. It's not as simple as before. I mean, even when I cross out the 1/2 and everything. What you don't see on this page, what I'm really trying to say, and I promise I'll move on, but what you don't see on this page anywhere, or this page, what you don't see is 1fmv squared equals 1fkx squared, because that was never a law. That was just something that happened to turn out to be the case. In the other problem, in the extreme case of comparing a 0 kinetic energy spot to a 0 potential energy spot, those are extreme cases. In general, oh, okay, yeah, I'll get you in 1 second. So I'm just saying, so, and I'm saying this because for some reason, like people tend, and maybe because it's like all over the web in some weird way, I'm just trying to say that yes, problem 4 and problem 5 are the same problem. Yes, you can use the same principle and the same procedure to solve both of them, but we all need to realize that the principle that we're using is total energy equals total energy. The principle is not kinetic equals potential, because that never was a principle. Don't memorize that. It ain't true. Bottom line, and then Andy or whoever has your hand, I think I'm not even looking, I just heard the sound. Bottom line, I think here, yeah, you could see the math. Here you're going to get 2 answers, plus or minus 0.095 meters. I believe that's a correct answer, right? I just want to say this is not to shame anybody or anything. This is just like education. If you got the answer 0.116, if you got the answer 0.116, you are not alone. You're not crazy. You're not a bad person, right? You're in very wide, vast company over the years. If you got 0.116, I get it. But why you did is because somehow you said 1f(x squared kx squared equals 1f(mv squared). So like you're the one I'm talking. If you got 0.116, you just want to gently and calmly at home rethink this and redo it until you understand what I'm saying. And then of course you can get all the points and all that. But I'm specifically talking to those of you who got 0.116. The reason is that you dropped a term. Okay, sorry, Annie. Yes.
So based on your recommendation that we should postpone like plugging in numbers, do you prefer us to just keep the 0 and not like cross it out? I don't know. That's a preference thing,
Yeah,
but
no, I mean, I think I understand what you're asking. Well, I think no, so honestly, I know this is going to sound weird, but when I say postpone the numbers, I mean, I don't mean numbers like 0. Like what 0 is whatever we can. I like to do the zeros early. Like, I mean, right. It's just a preference. It's just a strategy. We, I want to do the algebra before the numbers, but I want the algebra to be as simple and doable as it could possibly be, or the calculus or the trig. So it is a physics, it tends to be the physics taste, the physics strategy to look for zeros whenever we can so we can get equations as simple as we can to work with. But then once we've looked for the zeros and we've dropped out those terms, right, then all other kind of fancy numbers we postpone is, so I'm not really counting zero as a number. I'm counting it as an elimination of algebra terms. Does that make sense?
Yeah, that makes sense.
Okay, thanks. But it's a good question. And yeah, sidebar also, like on these kind of questions, or whatever, like hopefully people are sort of noticing too. I mean, yeah, and again, I always say this because I'm so defensive. Like every class, the ratio of straight up physics to other stuff will be higher and higher. And you'll see every class, believe me, the physics is going to get more and more mathematical, more abstract. It will, for all, I mean, I think you'll all see that soon. But I also want to say, so because this is physics 204, the math does get more intense. Like this will be much more calculus oriented, like in a few minutes. In fact, like, certainly by question nine, like those of you who've already noticed, by question nine, we're already into differential equations. So something really does happen with the calculus in this class. But also, at the same time, what I'm really trying to do with you guys now that you're all past physics 203 and here's, and yes, I'm trying to give you kind of like the pro tips or the taste techniques that people really use when they're like really doing physics a little bit more than I did last. Like, so of course, to some of it is take it or leave it, uh, but some of it is like you do find that the more you imitate, I find that the more that I imitate like my physics heroes or like how they tried to clean up their work or keep their work clean as they went, like the more able I am to solve harder problems. I mean, it's just so part of this class is like bringing this to a higher level of physics taste. But anyway, okay, so that's step five. Those are the two answers to step five. If there's any other questions, okay, 4:12. So we have 8 minutes. So now I'm going to sort of like I did yesterday, I guess. I mean, Monday, I'm going to give you the answers to the next three, like no step methods, no nothing, just the answers. So I can get us ready to launch into question nine, which is like really where things happen. Now question 6 and 7, I'm literally just giving answers but you don't, right? You give me the work. Let me say, question 6 and 7, many of us probably could just see in our head, or we guessed that that would make sense, and we'd be right. Like question 6, we already talked about with Annie. But what I was trying to say to her question 6, you literally now you need to show me the step method or whatever. I want you to see that question 6, you literally can show. I think there's supposed to be a negative sign there. I'm sorry. There's supposed to be a negative sign. I think. You can literally show that the answer to question 6 is what it is by doing, again, 1f mv squared plus 1f kx squared equals 1f mv squared plus 1f kx squared, and solving, as the question asks, for the other place where v is 0. Like, you already know one place is where the potential energy is 1/2 times 200 times 0.15 squared, right? The potential energy is 1f kx squared. So one place where v equals 0 is the starting place of this whole problem, 0.15 meters. So the potential energy is 1/2 times 200 times 0.15 squared, but that squared. But you're looking for another place that had the other place where V is 0, the other place where kinetic energy is 0. So it has to be the other X value that yields the same potential energy of 1 FKX squared. So it's literally the other root of that same quadratic. Right? So if one answer that was already known was 0.15, the other answer literally is negative 0.15. But I'm saying you can literally show mathematically that that has to be the case, assuming that energy is conserved from place to place, right? So you get negative 0.15. I mean, that's the answer. Now, at this point already, well, and in fact, I shouldn't even say, sorry, that's a slightly different question from the truth of the matter is, I believe Andy was asking, like, is it fair to believe that the farthest the thing ever gets will be 0.15 or negative 0.15? And I'm saying yes. Now, this question's actually asking, I guess, a slightly different thing. It's asking, how far will it get when it goes to the other side? So she already established it's not going to get farther. than 0.15. Now the question's asking sort of, will it get all the way there? And I'm saying yes. And you, whoever you, anybody might be saying, really? I mean, because I was in the lab and like when I let the mask go, I mean, again, this sort of gets back to last week, but you could be saying, but in the lab, like I let the thing go from over here. It didn't really go all the way to the other side. Did it really? Right? Fair point. Hold that thought for a second. And but if you're just kind of like, well, I guess I see the math. I don't know what other number I'd come up with. So okay, but it seems a little bit pushy to me. Then the next question, question 7, is really the same question again, but not right because now it asks, well, how many times is it going to do this? Like, will it go from 0.15 to negative 0.15 and then back to 0.15? And like, how many times can it really complete that full cycle? And I'm saying the answer is infinity. Now, by this point, you might definitely go, whoa, whoa, really? Infinity, Averbaum? I mean, now it seems off the charts, like unhinged, right? Like it was one thing when I was doing all these numbers and getting 3.87. That sounded like science, 3.87. But now you're saying perfect, perfect forever? Okay, so here's my point. No, I mean, of course, your spring in the lab is not so perfect. It didn't meet all the conditions that doesn't really even, I mean, it's a city university budget. I don't know what to tell you. Like, it's not NASA. We're not right, we're not like all competing for a Nobel Prize. So we've got these rinky, and I'm not trying to criticize, but yeah, we've got these rinky-dink springs in the lab that are meant to demonstrate sort of exercises and it's pretty easy. And then the springs are nice, they're good, but they're actually pretty massive compared to the mass that you put on the end of them. So already they're kind of not meeting one of the conditions of a really good spring. And then they're kind of short. And we're asking them to stretch back and forth for distances that are kind of long compared to how short they are. Now, again, it doesn't mean that for a lot more money we couldn't get a much better spring, but we didn't. Um, so in the lab, the springs are not really doing they're meeting some conditions enough to get some data. They're not really meeting all these conditions, but here's where I'm going with this. That means that the springs in the lab, they're very much not perfect. Make no mistake. They're not perfect. Therefore, they're not getting infinity for question 7. And they're not getting perfectly negative 0.15 for question 6. But please understand, therefore, the springs in the lab also wouldn't get perfect 3.87 for the velocity, for the speed at equilibrium. What I'm saying is this. It looks like question 6 and question 7 are suddenly like a big freaking lie. They're sort of a lie, but they are not any bigger of a lie than question 5 or question 4. Question 6 and question 7 are just exactly assuming the exact same thing that question 4 and 5 are, which is that energy is conserved, i.e., that there's really no friction, that really we're assuming that no non-conservative forces are doing, like friction, are doing any kind of work to take away any kind of kinetic energy that won't come back as stored potential energy. Like, in other words, I'm saying don't be fooled by super precise math into thinking that just because it's super precise, it's any more accurate than English. It isn't. All of 4, 5, 6, and 7 are all assuming something that is conserving energy, that all the forces doing work are conservative. To the extent that there may be non-conservative forces like too heavy of a spring or too short of a spring or too much friction, then sure, there's going to be degeneration in all of these, imperfection of all these answers. So that's why, yes, this is a math theoretical homework, not an experimental lab result. But they're all of this 4, 5, 6, and 7, all are the consequences of energy conservation, which we believe happens to well-behaved springs. Okay. There's 1 minute. I'm just gonna say, question 8, we will discuss on Monday. I'm just saying it just so you know. And again, even though it's English, you should show work and show thoughts because a lot of people had good enough thoughts quick enough that they got answers 1 and 2 correct, but a lot of people, the new stuff, the harder stuff, the thing you never thought about before, derivative of acceleration. A lot of people said wrong things for that. Of course, I wouldn't, that's fine, but they didn't give any kind of reason or anything. The more you do the steps and think this through with reason, the more likely it is that maybe actually you would get the last question right, which I think it's the answer is it's going up, not remaining constant. A lot of people say ring of okay, but it's 420. So the lab spring is vertical. Yes, it is. Wait, so do I care? Well, that's interesting. We can all that's interesting. I don't think that changes. I mean, that is a good point, and there's reasons for that. If you want to hang out for a second, I can address that more, but or not. Totally up to you. But I'm good for now. If you guys are good, I will not leave. I'll hang out if there's any questions, but I'll stop the recording and keep on keeping on, and I'll see you Monday. Thank you. Yes, thank you. Great.